So let us move over to the next topic of this course. So essentially we talk about continuous groups. Some of the examples of continuous group is SO2. SO2 is, let's say SO2, which is given by matrix, a 2 by 2 matrix, such that A transpose A is equal to identity and determinant of A is equal to +1. A transpose A is identity and determinant of A is equal to +1. Then we can talk about O2, which is 2 by 2 matrix such that A transpose A is equal to identity. The determinant is not necessary to be +1. It can be +1 or -1. Then we have SU2. This is actually a real 2 by 2 matrix, and here you have a complex 2 by 2 matrix. Complex 2 by 2 matrix such that A dagger A is equal to identity and determinant of A is equal to +1. Then you have U2, which is a complex 2 by 2 matrix such that A dagger A is equal to identity. Then we have SO3, which is 3 by 3 real matrix such that A transpose A is equal to identity and determinant of A is equal to 1. Then correspondingly we have O3, A transpose A is equal to identity. Okay. Determinant of A is +1. For SO2, for SO3, for SU2, it should be +1. This is called special orthogonal or special unitary. Special is because determinant is 1. So these are some groups, but there are also groups like GL of n comma r. Okay, this is set of n cross n real matrices. This is called general linear group, set of n cross n real matrices. Then you can have SL of NR. This is set of n real matrices with determinant 1. If the matrices you consider them to be such that their determinant is 1, then you have a name called SL of NR. Okay, so these are some examples of continuous groups. in every group there is a set of parameters whose variation will define different elements of the group. So a continuous group has a set of continuously varying parameters. For example, SO2 has got cos theta minus sin theta, cos theta, such that 0 less than or equal to theta less than 2 pi. So here theta is the parameter. And theta, what is the set on which this theta varies, or what is the space? It's called the parameter space. Okay, usually it's not a space, so you call that as group manifold. Group manifold for SO2 is S2, S1. What is S1? In mathematics, S1 is a circle. S1 is a circle. So theta will vary on the circle. Okay, so the space on which theta varies is called the group manifold, and that is S1 for SO2. S1 is a circle. So theta goes from 0 to 2 pi. That means it will be on the circumference of a circle. And similarly, other groups will have their respective parameters. So there is a continuous variation of parameters that give rise to different group elements. Now, what is the identity element here? Suppose if I call this as A of theta is equal to this. Identity A of 0 is the identity. A of 0 is the identity. What about inverse? A of theta inverse will be A of minus theta. What is A of minus theta? A of 2 pi minus theta. Correct? All these operations of theta, addition of angles, is modulo 2 pi. Okay, so if I write A of theta into A of phi, this is nothing but A of theta plus phi. So this is addition modulo 2 pi. This addition is addition modulo 2 pi. Is this abelian? A of theta A phi A theta is theta plus phi or phi plus theta. So SO2 is an abelian group. SO2 is an abelian group. What can we say about the classes? If it is an abelian group, every element is a class by itself, correct? So each element is a class. So how many number of classes are there? Infinite number of classes are there. Uncountably infinite number of classes are there. What is the center of this group? Entire group is the center because this is an abelian group. What is the commutator? Commutator group is only the identity. Only identity is the commutator. Whenever you have an abelian group, this is the case. The commutator group is just an abelian, just the identity element. Since each class is an element by itself, what can we say? We have only one-dimensional irreducible representations. All irreducible representations are one-dimensional. Okay? Since SO2 is abelian, all irreducible representations are one-dimensional. All irreducible representations are one-dimensional. Now, one-dimensional means they are actually some numbers, some complex numbers in general. So, what kind of complex number I should choose? If I choose a complex number for a particular representation, then their group multiplication should have this property. When I multiply two numbers, I should get a number where the argument is summed. So I must take something like, so possible representation form is e power some kind of a c into phi, something like that I can take. But then this representation should satisfy this property, e into c phi plus 2 pi should be equal to e into c phi. This property should be satisfied because this is a mod. Yeah, I think I will get it. So I want e power c into 2 pi should be 1, correct? That implies c 2 pi should be equal to I m so c should be equal to I m. If I have c as I m, some integer, then I will get it. So the representations are of this. So d m